In this video, we'll continue to look at the analysis and design of reinforced concrete columns. Now, as we mentioned earlier in the video, if the load is acting eccentrically in a reinforced concrete column, as you can see here, the vertical load NU is acting at an eccentricity of E. So that means we can simplify this column loading system into this system where we have moved the vertical load to the center. That means we need to have an extra moment M, which is equal to NU multiplied by E. That means this load system is equivalent to this load system where the vertical load is acting at the center of the column, plus we have a bending moment that is equal to NU multiplied by E because of the eccentricity of the loading in the column. So if we plot the load capacity and eccentricity of the column, we'll get a curve something like this one. So NU naught is where there is no eccentricity. That means the load is acting at the center exactly without any eccentricity, NU naught. That means there is no moment and the load capacity is purely the axial load capacity of the column. Now, as the eccentricity increases, as the load eccentricity increases, that means the E parameter increases, then the axial load capacity will decrease with the increase in eccentricity. As you can see here, the axial load capacity at an eccentricity of E is equal to NU, which is less than NU naught. So with increase in eccentricity, your axial load capacity will decrease in the column. Now put it in a different way. So if you are plotting axial load and moment capacity of the column, we see that when there is zero eccentricity, that means the moment is zero. Your axial load capacity is purely axial capacity of the column, that is denoted as NU naught. Now, as the moment increases or the eccentricity increases, your axial load capacity decreases as shown by this curve. So for the column, instead of finding just the axial load capacity, we need to find the combination of the bending moment and the axial load capacity together, because the moment acting on the column will affect the axial load capacity as well. So instead of just finding what is the axial load capacity of a column, we need to find a failure envelope that will consider both the axial load and the bending moment capacity of the column. And this diagram shows us the failure envelope that takes into account both the combination of axial load and bending moment in the column. And in this figure, if the column is subjected to pure bending moment, that means there is no axial load, then the capacity is MU naught. So the first case, when NU naught, as we described before, the column is subjected to the vertical load without any eccentricity, your capacity is NU naught. And if the column is subjected to pure bending moment without any axial load, your moment capacity of the column is MU naught. So in that case, your column is acting pretty much like a beam. So it is only carrying a bending moment only. There is no axial load. So the pure flexure capacity of the column is MU naught, which is denoted by MU naught here. That means there is no axial load acting on the column, right? So MU naught. And in between that, when there is a combination of axial load and moment, we plot this failure envelope for the column. And if anything, if your M star N star, that means the external bending moment and the external axial load falls within that graph, that means your column is safe. And if your external load and the moment falls outside the graph or the failure envelope, that means your column will fail. So instead of just finding one capacity, you have to draw the failure envelope that takes into account both the axial load capacity and the bending moment capacity for the columns. Now for the columns, the moments are calculated about the plastic centroid of the section. And the plastic centroid is the point in the column, like this one, where if the axial load acts on it at the plastic centroid, it produces uniform axial strain without any flexural strain. That means plastic centroid is a point in the column where if the axial load acts on it, there won't be any bending moment, there will be pure axial compression only. And for a symmetrical column, the plastic centroid is the geometrical centroid are the same. So example, in this case, the plastic centroid and the geometrical centroid are the same because the column is symmetrical as well. So now in this case, the load is not acting at the plastic centroid, it is acting at an eccentricity of E. So there will be a bending moment. So if we draw that one, it will look like this. So if we move this axial load to the plastic centroid, there is a corresponding bending moment, which is equal to mu equals to nu into A because of the eccentricity. So the moment is the axial load nu multiplied by the eccentricity E. So in this loading system is the vertical load acting at the centroid plus the bending moment nu multiplied by E. So now looking at this loading system, we can see how we can analyze this reinforced concrete member subjected to both flexure load and the axial load as well. So as you can see, if there is a bending moment acting on this column, that means this portion of the column will be in compression because it is the column is trying to bend this way. So that means this will be in compression and this side of the steel is in tension, right? And as a beam, as you can see, the top the left portion is in compression, and there is a compression block of concrete that is taking the compressive stresses, and the tensile stresses on the right hand side are taking the tension stresses now, right? It is very much like a beam, except that there is axial load nu also acting on that column, unlike the beams. Now, so as described earlier, the steel in here will take the tensile force. That means the steel here is taking the tensile force T, and this steel is at the effective depth of D if we consider from the topmost compressive fiber. So the depth up to the center of the reinforcement, as we did for the beam, is small d, which is effective depth. Now in the compression block, as you can see here, this is the compression block and this is taking the compressive stress. So here we have the compressive block, compressive stress acting in the concrete block, and the total compressive force taken by the concrete block is if denoted by Cc. And also we have the reinforcement in the compression side as well. So it is like a doubly reinforced section where we have the reinforcement in the compression side as well. So this reinforcement is in compression as well. So it is taking a compressive force. Cs is the compressive force taken by the steel in compression, whereas T is the tensile force taken by the steel in the tension side. So again, this is in tension side, this is in compression side. So we have two compressive force. Cc is the compressive force taken by the concrete block in compression. Cs is the compressive force taken by the steel in compression. And we have one tensile force where T is the force taken by the steel in tension. Now, as we did for the doubly reinforced section, the depth of this compression block is denoted as gamma KUD. And we know that the effective cover for the compression reinforcement, if we denote as DSC, this is D over 2, and the distance from the compression force CC to the center of the column is D by 2 minus A by 2, where A is the gamma KUD, right? So we use these dimensions to calculate the moment later on. So it is pretty much like doubly reinforced beam. The only difference is that apart from bending moment, this column is also carrying the vertical load Nu. So that is the only difference. Otherwise, it is very much like a doubly reinforced beam. The axial load capacity of the column is affected by the bending moment acting on the column as well. So we have to find out for this bending moment, this is the axial load capacity, and for another bending moment, your axial load capacity will be different. So we have to draw the failure envelope itself. Now, to draw the failure envelope, there are four critical points that we need to find out to draw this failure envelope, or it is called as a MN interaction diagram. M for bending moment and N stands for the axial load, so it is also called as the MN interaction diagram. So to draw that, the first point of interest is pure axial compression. Now this is the pure axial compression. In the y-axis we have axial load N, and in the x-axis we have the bending moment M. So the first point of interest is point A, where we are finding the pure axial compressive capacity of the column. So that means if there is no bending moment acting on the column, if there is no eccentricity of the load, and the load is acting exactly at the plastic centroid of the column, then it is subjected to pure axial compression, and Nu0 denotes the pure axial compressive strength of the column. Right? So that means in this column it is subjected to pure axial compression and the load is acting at the plastic centroid. And if that is the case, the strain diagram of the column looks like this one. So it is the column, all over column is subjected to pure axial strain, which is equal to epsilon c equals to 0.0025. That is corresponding to alpha 1 fc dash. Right? Now second point of interest is point B. As we have the combination of bending moment now and the axial force as well at point B, so as we know, so for example, if this is the column and we have the axial force and we have the bending moment as well. So for example, this is your bending moment and your axial force. Now, because this portion is in tension, this portion is in compression, the steel in the tension is carrying the tensile stress, steel in the compression is carrying the compressive stress. Now we know that the stress-strain diagram, the strain diagram of this section will look something like this, as we did it for the beam. So this is the steel strain, this is your concrete strain, and when it's crossing, it is epsilon Cu. And apart from that, there is a compressive strain in the compression as well, epsilon Sc. Compressive strain in the compression reinforcement. This is the tensile strain in the tension reinforcement. Now, the point B is called as a balance failure, and as we look at the beam, it is the same balance failure here as well. That means in the balance failure mode, the strain, the tensile strain in the tension reinforcement here reaches epsilon Sy. That means epsilon St, the steel tensile strain, reaches epsilon Sy, and the concrete strain at the top compression fiber, this one, reaches 0.003, or the crushing compression strain in the concrete at the same time. So the balance failure is achieved where the concrete crushes and the steel yields exactly at the same time. So this is the balance failure point, and that is another point of interest. So at the balance failure, we need to find out what is your axial load capacity. We denote as NUB, B standing for your axial load capacity, and MUB is the bending moment capacity at the balance point. Now if you find that, it will give us this point as well, right? MUB comma NUB will give us this point B as well. That's the balance point. That's the second point of interest for us. Now the third point of interest is here, point C, where there is no axial force and we are finding pure bending moment capacity of the column. That means there is no axial force in that case. So this column, where this is the compression reinforcement, this is your tensile reinforcement, and it is subjected to pure bending moment only, which is denoted as mu0, and there is no axial force in this case. So the pure bending moment capacity of the column is same as the pure bending capacity of the beam of that section, isn't it? So it is exactly like the beam now. There is no axial force, it is behaving like a beam. So we can find out what is the pure flexural capacity of a doubly reinforced section, because there is a reinforcement in compression as well as there is a reinforcement in tension. So we can find out what is your mu0, and that mu0 will give you this point. And that point is our third point of interest, that is called as pure flexural failure capacity of the column. Right, so we have now 3 points of interest, A, B, and C. Now for point C, where it is subjected to pure flexural stresses, now we can see that epsilon Cu is the crushing strain of concrete at the topmost fiber, like beam, and epsilon St is greater than epsilon Sy. If it is yielding, this steel is yielding, that is epsilon St is greater than epsilon Sy, and we have the strain in the compressive strain steel is epsilon, we can write epsilon SC, right? So that is the strain condition for pure flexural failure. Now the final point that we need to draw this MN interaction diagram is point D, where it is a pure tension failure. So that means this is compression, and below this one is tension. That means the column is now subjected to tensile force. As you can see here, for example, now the same column that we are looking at, and these are the reinforcement in top and bottom. Now this column is subjected to pure axial tension only. That means the force is acting like this. So there is a tensile force acting on here. So let's write it as NUT, that is the pure axial tension capacity. So there is no eccentricity, so that means the column is subjected to pure axial tension. And when it is subjected to axial tension, then all the stress is taken by the steel alone, because the concrete cannot take any tensile stresses. So all the stress is taken by the steel alone, and you can see the pure tensile capacity is denoted as negative, as we are taking compression as positive. So with these 4 points, now we can draw the MN interaction diagram, or the MN failure envelope for the column. So that is our point of interest here. So we'll see how we can find these 4 coordinates to draw the MN interaction diagram now. And in the failure envelope as shown here, the typical design region for the column is this one. So that means the axial load and the moment is below the balance failure point. That means the column is still ductile and Ku is less than Kub. Above that one, when Ku is greater than Kub, there can be a brittle failure in the column. So this region is your typical design region, but anything within this failure envelope, if the load and the moment is within that failure envelope, the column is safe, and if anything falls outside of this failure envelope, your column will fail. Now, to find these 4 points of interest to draw the MN interaction diagram, the first point, as I said, is point A, which is a pure compressive capacity of the column, NU naught. And to find MU naught, there is no bending moment acting on that point, so M is 0 at that point, and the pure axial compressive capacity, as we have denoted by the equation in the last video, it is represented as NU naught equals to the compressive force taken by the concrete plus the compressive force taken by the steel, right? So in the column there are steel and the concrete as well, so the compressive force is taken by both concrete and steel. So the compressive force that is taken by the steel is area of steel multiplied by FSY. Now if this is your column and you have 4 reinforcement, and area of steel AS is all of these 4 reinforcements, area of all the 4 reinforcements, and multiplied by the yield strength of the steel, that will give you the compressive force taken by the steel. Now the compressive force is also taken by the concrete as well, so the area of the concrete that takes the force is gross area AG minus area of steel. So that is the area of concrete that takes the compressive force, isn't it? So let's write it as AC. That's the area of concrete that is taking the compressive force, gross area minus the area of steel. Now if we multiply this one with FC dash, that is the compressive strength of the concrete, that gives us the compressive force taken by the concrete, right? But to take the size effect into account, instead of just using FC dash, we take alpha 1 factor in here as well. Now alpha 1 is taken into account to account the size effect on the compressive strength of the column. Now because FC dash is determined using the small cylinders, 100 millimeter diameter by 200 millimeter length cylinders. So the strength of the concrete found out from the concrete cylinders may not be exactly same as the compressive strength of concrete in the columns, which are much larger than the cylinders. In the columns, there is a tendency that the concrete will segregate, so the concrete strength may not be as same as denoted by the small cylinders. That's why alpha 1 factor is taken to reduce the capacity of compressive capacity of concrete given by the cylinders, to take into account the size effect in the columns, right? So that's why alpha 1 factor comes in. So alpha 1 is given by 1.0 minus 0.003 FC dash. It is given by clause 10.6.2.2. Now putting back the alpha 1, this is the force taken by the concrete, and the force taken by the steel is AS multiplied by FSY. So if we add these two things, it gives us the axial compressive capacity of the concrete. And that's the pure axial compressive capacity when there is no bending moment acting, that is mu equals to 0. There is no bending moment acting at that point. And before we go into the point B, that is the balance failure mode, and point C, that is pure flexural mode, we can easily find out point D first. So let's go into that one first. The point D is the pure tension failure, isn't it? So that is denoted as NUT. So that means the concrete is subjected to pure axial tension, and when the column is subjected to pure axial tension, then the concrete will not take any tension forces. All the steel is taking the tension stresses. That means the capacity of the column in tension is given by area of steel multiplied by FSY. Now area of steel, again, we take into account all the 4 reinforcement in this example. So all of the area of that 4 reinforcement is AS multiplied by FSY. That gives us the tensile capacity of the concrete column, because we are not taking the contribution of the concrete in the tension capacity. We found out point A, which is, so in the moment interaction diagram, so this is your axial force, this is your bending moment. So we found out point A, which is a pure axial compressive capacity given by NU naught. And second one, we found out the pure tensile capacity denoted by NUT, point D. Now we are trying to find point C here, which is the pure bending moment capacity denoted by mu naught. So at point C, there is no axial force acting on it. That means N equals to 0. There is no axial force, and it is pure bending moment capacity of the column. That means your column can be treated pretty much like a beam. And as there are reinforcement in both compression and the tension side, we have to treat it as a doubly reinforced section. So as you can see here, this is a column, but as it is subjected to pure bending moment, mu naught, so there is no axial force. When the column is subjected to pure bending moment, that means as the moment is like this is in tension, this is in compression, this steel area is taking the tensile stresses, this steel is in compression, so it is taking compressive stresses. So we denote the area of steel in compression as ASC. We denote the area of steel in tension as AST. And the top part of the concrete block here is taking the compressive stresses. So if we draw the strain diagram, it is exactly like the doubly reinforced section. So we can see that the depth of the neutral axis here, so this is your neutral axis, is KUD, and the this should be up to here only, so please correct it. So depth of your compression blocks is gamma KUD, so up to here, and the width of the compression block is alpha to FC dash, and the tensile stress in the tension steel is, because it is yielding, we are assuming it is yielding, it is FSY. Now the compressive stress in the compression reinforcement we denote as sigma SC. So it is like a doubly reinforced section. So if we look at the force profile, again like a doubly reinforced section, the tension force in the tension reinforcement is T. The volume of the compression block is CC, that denotes the compressive force taken by the concrete block, CC, and CS denotes the compressive force taken by the steel in compression. So we have 3 forces now, and we can analyze exactly like the beam to find what is your ultimate moment capacity. So now the fourth point that we are interested in is the balance failure point. So we already have found the 3 points here. So let's write it down again. So this is axial force, this is bending moment. So we are trying to draw the MN interaction diagram, or the Feller envelope for the column. So first one we found out, which is NU naught, that is pure axial compression capacity. Second one we found out is pure tensile capacity of the column, that is NUT. Third we found out is point C, which is pure bending capacity. There is no axial load in point C. Now the fourth point that we need is the balance failure, which is point B, where the steel in tension is yielding and the compression fiber in concrete is crushing, that is epsilon Cu is 0.003, and that is the point B. So once we have these 4 points, we can draw the MN interaction diagram for the column. So how to find point B? So you see that for point B, if we draw the stress strain diagram, that means the tension steel is just yielding at the balance failure, that is epsilon St is equal to epsilon Sy, and the concrete has just started crushing. That means the compressive strain in concrete, the topmost fiber in concrete, is 0.003. So using the similar triangles here, we can easily find out what is your KUB, that is neutral axis parameter for balance failure, that is KUB can be easily found out. So we have done that one for the balance section for the beam. So if you go back and review that, we know that the balance failure, so KUB is denoted by epsilon Cu, which is the crushing compression strain in concrete, that is 0.003, and epsilon Sy plus epsilon Cu, where epsilon Sy denotes the yield strain in steel. So epsilon Cu is the crushing strain of concrete, which is 0.003, and epsilon Sy is the yield strain of steel, which is 0.0025. Again, this one is 0.003. So we can find KUB easily here. So KUB will come out as 0.545 for 500 megapascal steel. So with this information, we can find out what is the moment and axial load capacity at the balance failure, because at the balance failure we have the axial load as well as the bending moment as well. So we need to find out what is NUB and MUB as well. So with this information we can find out. So for simplicity, let's denote this depth of this compression block, which is we normally denote as gamma KUBD. We denote it as AB, that is the depth of the compression block at balance failure. So we just denote it just to make it the expression a bit shorter. So we can analyze that to find out the moment and the axial load at the balance failure. So at the balance failure, as you can see in the stress strain diagram, the steel in tension is just yielding, that is E epsilon St is equal to epsilon Sy. The concrete in the topmost fiber is just crushing, that is epsilon Cu equals to 0.003. Now the stress diagram will look like this. The steel is yielding, so stress in the steel is Fsy, it is just yielding, and the depth of the compression block is again gamma KUBD, and the steel in compression is taking sigma Sc stress as well. Now we have the two forces in compression. Cs is the compression force taken by the steel, Cc is the compression force taken by the concrete block, and T is the tension force taken by the steel. Now it is again exactly like a doubly reinforced section at the balance failure point, but the only difference is that there is axial load NUB acting on the column as well. So for the horizontal equilibrium of the forces, NUB, that is the center of the column, should be equal to the compressive force taken by the steel plus compressive force taken by the concrete minus the tensile force taken by the steel, T, right? So that will give you the axial load capacity. Now in here, the compressive force taken by the steel is equal to area of steel ASC multiplied by stress in this compressive steel, which is sigma Sc. Good. Now Cc is the compressive force taken by the concrete here, so it is the volume of that equivalent stress block diagram, which is equal to alpha 2 Fc dash gamma KUDB, where gamma KUBD is written as AB, so just to shorten the expression, so we are writing as AB, and multiplied by the width of the beam B, minus the tensile force here is equal to area of steel AST multiplied by, yes, it is yielding, it is FSY. So that is the expression for your balance failure load NUB. So that's exactly what we have written it here, right? So there are 4 forces, so NUB should be equal to this CS plus CC minus T. Now to find the balance moment capacity, so we can take the moment at the centroid of the column. That means we don't have to consider this vertical force NUB acting because it passes through the centroid. So to take the bending moment capacity MUB, taking moment at centroid, so that means MUB should be equal to NUB multiplied by 0. There is no lever arm, so that's gone. So that means the compressive force taken by the concrete CC multiplied by this distance up to the centroid, which is D by 2 minus AB by 2, right? Where AB by 2 is the depth of the compression block. So AB by 2 is up to the center of the compression block. So that will give us D by 2 minus AB divided by 2 plus the moment due to the compression force in steel is also in anti-clockwise direction, so it is CS multiplied by this distance from center of the reinforcement to the centroid of the column, which is given as D by 2 minus DSC, where DSC is the effective cover of the reinforcement. So this is DSC, so this distance is D by 2 minus DSC. Good. And also the tensile force, the moment due to the tension force, is also in a clockwise, anti-clockwise direction. So that means we have to add that one as well. So the tension force multiplied by this distance, which is D minus D by 2. So D minus overall depth of the column divided by 2. So that gives us the moment capacity for the balance section. And if you write down the expression of CC, CS and T, you will get this equation, right? So this is nothing but T, this is nothing but CS, and this is nothing but CC. So with these equations, you can find out what is NUB and MUB. So now we have all the 4 points to draw the MN interaction diagram or the failure envelope for the column. So once we have the failure envelope for the column, that is our ultimate failure envelope, we need to multiply with 5 factor to get the design failure envelope as well. And the 5 factor is determined again from table 2.2.2. And we can use the 5 factors based on this one. So as you can see here, so bending with axial compression. So this will give you your 5 factors here based on whether NU is less than NUB or not. So you can get the 5 factors from here and use that one to find the design moment capacity or the axial load capacity. So based on that, we can find out the failure envelope for the design capacity. So N and M capacities here. So we found out these 4 points, A, B, C, and D. So this is your ultimate failure envelope, and if you multiply each one of them using the corresponding 5 factors, we will get, this is your phi NU naught, and this is your phi MUB and phi NUB, so balance failure, and this one is your phi MU naught, 0, and this point will be your 0, phi NUT. So we can plot the design capacities as shown here. So this will be your design failure envelope. This one was your ultimate failure envelope, but the blue one is your design failure envelope. And whatever the load that you have, M star comma N star should fall within that envelope, and then it is safe. Now, so the steps that we follow to find out the capacity of the column is as shown here. So the first part is we have to evaluate and plot the MN interaction diagram for the given section of the column. So for the given section, we have to draw the MN interaction diagram, that is the design capacity envelope, and then we plot the M star N star point. So the M star N star point based on your external bending moment and the external vertical load acting on the column. We find out using the load combination, we find out M star and N star and plot that point here. And if that point falls within this design failure envelope, then your column is safe. And if it fall outside, then it is unsafe. So we have drawn just the right side of this curve so far. That means we did this for the column where the bending moment is this way, but for the column, the horizontal load may act in both ways, isn't it? So for this column, the horizontal load can act on this way, or horizontal load can act this way as well, like wind or earthquake load can act in both ways. That means the bending moment can be this way, making it tension here, compression here, or if the load reverses, then the bending moment can be acting this way as well. That means tension is here and the compression is here. So we need to draw the moment interaction curve for both the sides, and if it is symmetrical, the MN interaction diagram will be symmetrical on both sides as well. Right? So take into account the reversal of load on the column, so the moment interaction diagram can be drawn on both sides. Now, the column is a three-dimensional member. That means the horizontal load can act on either face of the column. So instead of just having a two-dimensional MN interaction diagram, you can have a three-dimensional moment interaction diagram which takes into account the horizontal load acting on all the faces, all the four faces of the column, and the MN interaction diagram will look like this one. Of course, you will be needing the computer to draw this MN interaction diagram. Now, for the design of the columns, we usually get the design charts like this one. So as given in the concrete design handbook. So as an engineer, you'll have access to these kind of design charts, so that will help you to design the columns or beams much easily. This whole moment interaction curve, MN interaction curve, is for the column size of 400 by 400 millimeter columns. So for different size columns, you'll have a different sets of these design charts. For this one, it is 400 by 400 millimeter column, and the reinforcement ratio is 1%, 2%, 3%, and 4%. So each one of these curves denote different reinforcement ratios. The reinforcement ratio in the column is denoted by the total area of reinforcement, that takes into account all 6 reinforcement in this case, divided by the gross area of the column. So AS over AG is your reinforcement ratio, which is 1%, 2%, 3%, and 4% in this case. So now what we do is for the design of the column, we first find out what is the external bending moment acting on the column. So that is M star. So we need to find out using the load combinations and the load acting on the column. And we also find out what is the vertical load, maximum vertical load acting on the column, M star and N star. So first we have to find out these values using the load combination. So if M star is 170 kilonewton meter, and N star is, say for example in this case it is around 2700 kilonewton. So from the load combination we find out that the maximum bending moment acting on the column is 170 kilonewton meter, and the maximum vertical load acting on the column is, say, 2700 kilonewton. So we plot this coordinate in the design chart, and if we plot it, the x-axis is 170 and the y-axis is on 2700. So we find that your M star N star plot is here. Now we know that from the design charts, this green one is for 1% reinforcement. So that 1% reinforcement is not adequate because this would fall outside that. So we need at least the blue chart, either 2% or slightly less than 2%. So we exactly know what reinforcement is needed in this case. So if you provide 2% of reinforcement, then your column can take that M star N star force and moment. So for the design of the structural element subjected to axial load and moment, so the first thing that we need to do is we need to find out what is the M star and N star, the maximum bending moment and the maximum vertical load acting on the column using all the load combinations. Then we need to select a realistic geometry of the section. So we need to have the preliminary size of the columns. We need to define that. I'll come to that one in a moment. And then we refer to the relevant design chart based on the size of the column that we selected. So we need to refer to the corresponding relevant design charts and plot the demand M star N star point. So plot the demand, that means M star N star point, and choose the reinforcement ratio rho, which envelopes the demand. So make sure that you choose the reinforcement ratio rho so that M star N star falls within that envelope. So once the reinforcement ratio is known, so we can find out the total area of reinforcement required by rho multiplied by the gross area of the column. So we can find out what diameter of bars and how many bars are required. Now for the point 2, where we have to approximate the size of the column for the design, we can use this approximation method. So in this method, what we do is basically we consider the pure axial compression capacity of the column. Now for the pure axial compression capacity in U naught, you know that it is alpha 1 FC dash, gross area of concrete minus area of steel plus FSY AS, isn't it? This is the pure axial capacity of the concrete subjected to pure axial compression only. Nu naught can be written as N star divided by phi, isn't it? So phi is taken as 0.6 in this case in pure axial compression, phi, and alpha 1 we know, FC dash we know as well. And to simplify, we can neglect this area of steel subtraction. We can just use the area of gross steel only, plus FSY, and this can be written as rho multiplied by gross area of concrete, right? So with that equation you can find out what is the gross area of the column required for your given reinforcement ratio. So that means the gross area of concrete required is N star divided by phi. For compression it is generally taken as 0.6 multiplied by alpha 1 FC dash plus FSY into rho. So here rho is area of steel divided by gross area of the column. So once you know the gross area of the concrete column, so you can find out the size of the column by B bar multiplied by the D bar, where B is the width of the column and D is the depth of the column. B bar multiplied by D bar. Now to make sure that it is satisfied, the load capacity is satisfied, what we do is, after finding B bar and D bar, the width of the column that you take is 1.2 times whatever you find out here, and D is taken as 1.2 times whatever you find out here. So that will give us the rough estimate of the size of the column that we require, that will meet your gross area of column requirement according to the axial load capacity. Now just to keep in mind that even though the code does not specify the minimum size of the columns, but usually the minimum dimension of cast in place columns should not be less than 200 millimeter and preferably not less than 250 millimeter. So we need to keep the dimension more than 250 millimeter if it is a rectangular column, and if it's a circular column, we don't usually cast the column less than 300 millimeter size. So make sure that your column sizes are bigger than that. Now for the vertical reinforcement for the column, if we provide too little vertical reinforcement, the column might be vulnerable when it is subjected to impact loading or blast loading. So if there is an impact load on the column, then there is a risk that the reinforcement will actually snap and the column will fail. So if we have too little reinforcement, that can be a possibility, and that can be the danger. Now if we provide too many vertical reinforcement, as you can see in this figure, so if you have too many vertical reinforcement, it can create the congestion of the reinforcement, so that we can't properly compact the concrete, and that can lead into the honeycombing effect in the column as well. So we shouldn't be providing too little reinforcement, because it will make the column vulnerable to impact loading. And if we provide too many reinforcement, it can cause congestion of the reinforcement, so that we can't compact the concrete when we are pouring the concrete. So usually for the column, the reinforcement ratio, we put it between 0.01 to 0.04%, as you can see here. So AS by AG is nothing but the reinforcement ratio rho, and we keep it between 0.01 to 0.04. That means the rho is between 1% to 4%. So that means the reinforcement ratio, we keep it between 1 to 4% of the gross area of the concrete column. As we saw in the last video, in the columns, apart from the vertical reinforcement, we also have the lateral ties as well. These are called as the lateral ties. So they have multiple purposes. So one purpose of the lateral ties is that it will confine the concrete core and will improve the compressive strength of the concrete, as well as the ductility of the column as well. And secondly, it will help to prevent the longitudinal reinforcement from buckling as well. Now if this the distance between the lateral ties is too large, the longitudinal steel subjected to compressive stress can buckle out as well. So it can buckle out like this one, right? Because it is subject to compressive stress, so it can buckle out as this one. So we need to make sure that the lateral ties are within the specified spacing, maximum spacing, S max, so that the longitudinal reinforcement do not buckle. So AS3600 gives the provision for the size of the lateral ties, as well as the maximum distance between the lateral ties as well. So the size of the lateral ties is to make sure that it can confine the concrete core and doesn't let the concrete core burst. So it prevents the outward bursting of the concrete. So depending on the size of the longitudinal reinforcement, you need to select what size of lateral ties we need to provide. So for up to 20 millimeter longitudinal reinforcement, you need to provide at least 6 millimeter of the lateral ties. And if the column reinforcement is bigger, that is 24 to 28 millimeter, you need to provide at least 10 millimeter lateral ties. And to prevent the buckling of the longitudinal reinforcements, the maximum distance between the lateral ties, that is S max, should be smaller than DC, that is the minimum dimension of the column, or 15 times the diameter of the longitudinal bar. So that will give you what is the maximum distance between the lateral ties that you can provide. Now if you do not provide adequate lateral ties, this kind of failures can occur. So in this case, as you can see, the lateral ties are not big enough, so the concrete core is damaged here. Core is being damaged, and once the concrete core is damaged, your integrity of the column is compromised and the structure will fail. And in this case, in the right hand side picture, as you can see, the distance between the lateral ties is quite big. So the S is quite big here. So that means the lateral ties are not adequate to prevent the buckling of the longitudinal reinforcement. So you can see that there is a buckling of the longitudinal reinforcement. So once there is a buckling of the longitudinal reinforcement, the concrete core will fail as well, and again it will compromise the strength of the column as well, so it cannot take any more load. So we have to make sure that the lateral ties have adequate diameter, as well as the spacing is kept within the maximum spacing allowed by the code as well.